Hello chemistry students, this is Dr. Tullis. We are starting the next chapter, which is looking at other aspects of aqueous equilibria. For this section, we will be able to predict the effect of the addition of a common ion on the pH of a solution of a weak acid or a weak base. We've examined the behavior of weak acids and bases in terms of equilibrium involving conjugate pairs. The pH of a solution was found via the Ka or the Kb. But what would happen to the pH of an acetic acid solution if you added a significant amount of its conjugate base, the acetate ion? The pH of the solution, which is now comprised of the weak acid and the conjugate base, is higher than the pH of the solution with only the weak acid by itself. The change of pH when a significant amount of conjugate base is present is an example of the common ion effect. The name comes from the fact that the added acetate ion is common to the ionization equilibrium reached of acetic acid. Let's look at this example. Let's say I have acetic acid in a water solution. We know that acetic acid's conjugate pair on the right is going to be the acetate ion, and we have water's conjugate pair is our hydronium ion. Let's say that we have 0.25 molar acetic acid. What is the pH? Now this is review, right? We would set up our ice table. We would say that we had 0.25 molar of our acetic acid. We know we have no products formed. We are going to lose reactant and gain product, giving me my equilibrium values as shown. And then we would look up the Ka value for acetic acid, which is 1.8 times 10 to the negative 5, is equal to x squared over 0.25 minus x. We would then take our Ka value and times it by 100 to see that it is way less than our initial concentration of 0.25, so we can cross off that minus x, making this a much easier equation to solve for x. And this would tell us that our x, or our hydronium ion concentration, is 0.0021 molar. We can then take the negative log of that concentration to get the pH. But let's say now that we add a significant amount of the conjugate base, which would be the acetate ion. So I wouldn't be starting at 0. Le Chatelier's principle predicts that when we add that common ion, it causes the reaction to proceed far less to the right, because right now it is proceeding to the right. So our hydronium ion concentration would be less than what we got in the presence of the added acetate ion. We can see here that our aqueous acetic acid has a pH of 2.7 and our sodium acetate has a pH of 9. When I mix the two together, this pH meter shows that the solution in the beaker has a lower hydronium ion concentration than the acetic acid solution. Let's look at a sample problem. What is the pH of a solution that contains 0.25 moles per liter of acetic acid and 0.1 moles per liter of sodium acetate? Let's set it up like we have before. We have our acetic acid plus water to give us our hydronium ion concentration and our acetate. And I'm starting initially with 0.25 moles of the acetic acid, and initially I'm starting with 0.1 moles per liter of our acetate. This is where the difference is coming from with our ice tables. Initially, before, I only started with reactant and I had no products. But with our buffered system, we are starting with some of our product. That's the conjugate base. So I will still lose reactant and gain product, but our equilibrium is going to look a little bit different. 0.25 minus x, our hydronium ion concentration is still x, but here my conjugate base is 0.1 plus x. We're still going to set it up the same way. Ka is equal to our products over our reactants. Our products are the concentration of H3O plus times the concentration of the conjugate base all over the concentration of acid. So when I plug in my x times 0.1 plus x over 0.25 minus x, I can still take my Ka, times it by 100, and I'm going to see that it is still way less than both of those initial concentrations. So I can disregard the minus x and the plus x. That lets me simplify, and now I can solve for x. X, which is my hydronium ion concentration, is 4.5 times 10 to the negative 5. If I take the negative log of that, I get a pH of 4.35. Some observations, we can still use that assumption that X is much less than our two initial concentrations, so we can drop that plus X and minus X. By having that 0.1 molar acetate ion has resulted in an increase of the pH from 2.67 to 4.35. Let's go back and look at that first example. Without any buffer, my acetic acid, originally containing 0.25 molar, had a pH of 2.67. With 0.1 molar acetate initially added, my pH went from that 2.67 up to 4.35. So we took a base, that acetate ion, and it was added to the acidic solution. We can make a useful observation and say that adding a base to any solution will always result in an increase in pH. Here's another example. We have 0.3 molar solution of formic acid and have added enough sodium formate to make the solution 0.1 molar in the salt. Calculate the pH of the formic acid solution before and after adding the conjugate base. Let's look at the before first. We're going to set up our ice table like we are used to doing. I originally have 0.3 molar of the formic acid. Formic acid, again, in water to give me the formate ion and our H3O+. And I originally had none. So I took my equilibrium values, plugged it into my Ka, took my Ka, times it by 100, found that it was way less than the 0.3, so I can take off that minus X. Solved for X, took the negative log of it, and my original formic acid solution had a pH of 2.13. Now, let's look at the after. Same setup, but I added the 0.1 molar formate. I just dropped the Na. Remember, Na plus has no effect on the pH. So I dropped the Na here and just left the HCO2. Found our equilibrium values here. Again, I lost reactant, I gained product. Still found that 1.8 times 10 to the negative 4, the Ka, times it by 100, it needs to be less than both of those initial values. And because it is, I can drop the plus X and the minus X. And when I solve for X here, I got 5.4 times 10 to the negative 4th, took the negative log of it, and got 3.27. Again, my pH went from 2.13 to 3.27. When I add conjugate base, the pH increases. See if you can set up this ice table. Find the pH of a 0.25 molar NH3 solution. Did you get this set up? Your initial was 0.25. My ammonium on the right was 0. My hydroxide is 0. My Kb expression, because ammonia is a base, would give me my NH4 plus ammonium times the hydroxide all over NH3's value. So X squared is equal to 0.25 minus X, which is equal to 1.8 times 10 to the negative 5. That's the Kb value for NH3. If I took my Kb value and times it by 100, it is way less than that 0.25, so I can drop the minus X, do 0.25 times 1.8 times 10 to the negative 5, and then square root both sides to get a hydroxide ion concentration of 0.0021 molar. The negative log of that would give me the POH, which is 2.67, and then the pH would be 14 minus that, so I got 11.33 for a pH value of 0.25 molar NH3. Why don't you set this up? What is the pH of a solution made by adding equal volumes of 0.25 molar NH3 and 0.1 molar ammonium chloride? The only difference is that instead of starting with 0 ammonium, I have 0.1, so our equilibrium values will be 0.25 minus X. Over here is 0.1 plus X and X. Since there is more ammonia than ammonium present, the reaction will proceed to the right. I would set up my Kb expression of products over reactants just like we have done before. I took my Kb value, times it by 100, and found that it was way less than 0.25 or 0.1, so I was able to cross off the plus X and the minus X. And when I solve for X, which is the hydroxide ion concentration, I got 4.5 times 10 to the negative 5. The negative log of that would give me a POH of 4.35. So 14 minus that would give me a pH of 9.65. The pH before I had that common ion was 11.33. So the pH drops due to the common ion. And the common ion in this case was the conjugate acid. So when we add a conjugate acid, our pH drops. When we add a conjugate base, the pH increases.